today's discussion. The plan is probably we're going to wrap up the whole discussion in an hour, and then we're going to have a Q&A session after that. So before we actually start the final discussion on follower circuits frequency response, I'm going to briefly, just to remind you that we're going to have our final exam, which will be scheduled next Tuesday, which is 14th of June. And it will be within the class hours, so it'll be 2 hours, between 2 hours, from 10 to 12 p.m. And remember, it will be on EE class, once again. If you want more detail as to what will be inside or more detailed description of how to prepare for the final, we'll have an individual tape which will be available online as well. So the exam will be held online on E-class platform. And remember, there will be 3 sections to make sure that you can finish, you finish each one of them. So there will be 3 sessions of different time frame, and then we're going to have some break between the sessions, okay? So what will be covered mostly, according to our previous, it will be after all the material we covered after midterm 1. So that would include single stage amplifier, by MOSFET single stage amplifier. And then the second thing, of course, is we talked about cascade structure. And then we talked about current mirror. The key topics are cascade, current mirror, and then differential pair. And finally, frequency response. We will limit our analysis of frequency response because the discussion of frequency response in chapter 11 is fairly extensive, so frequency response will be limited to single stage amplifier. So these are the materials you should familiar yourself with and prepare to be, it will be included in the exams, okay? So, and what happened, I think on Tuesday, there's some technical issues, so the discussion ended before, the videotaping ended abruptly. So I'm going to sort of review what we have already discussed on single stage amplifier, and then we're going to, where we at and what we're going to talk about today to finish up the discussion. So we have already discussed, so for single stage amplifier, there's basically 3 types. So first of all, it's either common emitter, common source architecture. So based on common emitter and common source architecture, what will happen is that if you, I'm just simply going to use MOSFET as a simple analogy. So if you look at the effect of parasitic capacitance, we only talk about parasitic or high frequency, the high frequency response, meaning that we're not considering the low, you can also, we have already discussed the low frequency part, but inherently, if there's no blockage or DC setup needed, typically the bandwidth is limited by high frequency response. That is to be limited by parasitic effect, parasitic cap. So in this type of structure, what happened is that you look at the impact of the 2 main, if we limit our discussion on the 2 main capacitance, which is CGS, CGD. So this will lead to implication of having your omega P1, which is the dominant pole. So if I ask you to find the dominant pole of this architecture, you look for the input pole, because the input pole is typically the one that experience. So input pole will then be determined by Miller amplification. So this one was subject to Miller amplification. So what happened is that you then have a input capacitance, which will be CGS, plus the amplification GM R load times CGD. And then omega P1 will simply be Cin RS over 1. Okay? So that's typically the limiting frequency domain limiting factor, which is the dominant pole when we talk about high frequency, the turning point or corner frequency of common source amplifying. And you look for the largest capacitance, and typically this is the input capacitance being amplified by this Miller amplification effects. Okay, so that's what you typically see on a common source architecture, the frequency response of common source architecture. The second part, we look for common, common base or common gate. Okay, so for common base or common gate architecture, what happened is that there's no Miller amplification. My input port is here. This is the input. X, let's say, this is output. In V in V out. If that's the case, what are the parasitic capacitance? There's CGS, CGD, CGS. If I'm only looking at these two main capacitance, then omega n will be, if you're looking in from here, it will be Rn times CGS over 1, where Rn is dominated by 1 over Gm CGS. So this is a very high frequency pole if you're looking at the input terminal. If we're looking at the output terminal, I should say, it will then determine, let me just show you. Let's say I have an R load here. This will then experience also an R load. So the output terminal will then depend by the output resistance dominated by R load times CGD over 1. Okay? And because there's no amplification effect on parasitic capacitance, so these numbers can be comparable, meaning that it's harder to determine which one is the dominant pole. If you want to guess, mostly this one will typically be higher. Omega P out would typically be higher. It would, of course, depends on the setting, but mostly omega P out would typically be higher because R out would be slightly higher, but it's not that much a difference. So if in this kind of discussion, you probably want to list both input and output poles. Okay? So no Miller amplification in common gate or common base architecture. So we'll come to the last one, which we have started discussion, which is the follower circuit. So for the follower circuit, let's briefly review what we have already discussed last time, which is a emitter follower. So if you look at a emitter follower, there's a loading. And let's discuss the effect when it's driving a capacitance C load. So if this is the case, this is the example or the architecture we use to analyze the frequency response. So we know first by looking at this structure, we know that at low frequency, at very low frequency, what happens is that you don't see the effect of C load. So when omega approaching 0, which is close to DC, the voltage gain, we know that the voltage gain is approximately GM R out 1 plus GM R out. And because this is an ideal current source, let's assume that this is ideal. Let's say I1 is ideal. Therefore, you don't see the effect of C load, therefore R out close to infinite. Therefore, at DC, you see a gain close to 1. So we start with a gain close to 1. And then you could construct the small signal. Let me just draw the small signal. I'm not going to go through the derivation again. You can look it up from, on Tuesday's discussion. So there will be, if you look at this, it will be C mu. The small signal model will be something like this. I'll have my input here. And this will be a parallel C mu C pi. And then it will drive a capacitive load. There's two current that's feeding into emitter. One is collector current, the other is base current. Coming from the base. Current coming from the base consists of two parts. One is the DC base current. The other is the charging current feeding forward based on C pi. Okay, so through this small signal model, let me highlight the input and output. So I have in this circuit, I have my input at the base, output and the emitter. So based on this analysis, we can actually construct a transfer function. So I'm just going to give the final results. What happened is that we have a transfer function. So BL being the overall gain or transfer function of the circuit, well, then can be rearranged as this. You'll find a 0 and a pole in this circuit, where I'm just going to highlight the 0 will be at close to GM, and where the pole will be GM C pi plus C load. Okay? So what does this imply when you have a, so based on this, we get two results. One is that we know that omega p is, because this term is larger, we know C pi plus C low must be larger than C pi. Therefore, this should be smaller than omega z. And the ratio will be determined by its distance. The ratio will be determined by its distance. The second thing is that you can look at to do Bode plot once again. The other thing is that we know that the voltage gain at omega close to, I should just use the same. We already know that omega close to 0, you can either use this or that. It should be consistent, equals to square root 1 plus omega p squared. Square root 1 plus omega z squared. Okay? Let me just write this down in general terms. So the magnitude of the gain equals to that. So you look for two extreme cases. One is when frequency is very low, and you don't see this term, or let me rewrite. So once we have this expression, we can analyze the boundary. So let me write it down again. So if I have this magnitude, which is the transfer function looks something like this. Omega z squared 1 plus omega z squared. This is p, sorry. Okay? So you look at two conditions. One is when frequency is very high. When frequency is very, very low, sorry, omega z, much more smaller than omega z and omega p. What happens is that you don't see this term, and then this should be approaching 1. So this is consistent with our low frequency analysis where your follower circuit have an ideal gain of 1. So when frequency is very high, much larger than your 2 turning point, what happens is that this will then be approximated by, you ignore the 1, therefore you get omega p, omega z. Therefore, we get a ratio between omega p and omega z. This will give us c pi plus c load c pi. Okay? So if I give you an example, you should be able to do the Bode plot. So if I give you an example of the circuit, let's say I have C pi equals to 0.1 picofarad. I'm not driving a very high loading just to make our analysis. So let's say GM is 1 milliamp per volt. So based on this data, we should be able to get omega p is at 1 giga radius per second. And omega z will be at 10 times of that. So if I do the Bode plot, it will look something like this. Remember, you start at 1, gain of 1, which is 0 dB. And then once it hits pole will be at a lower frequency. Pole at 1 giga, 1 G. This is 10 G. So what happens is that you will get a transfer function look something like this. It will turn at its pole. There might be some gradual change, 3 dB. And then it will drop at a rate. When it hit a pole, it will drop at a rate of 20 dB per decade. And then afterwards, it should drop even further down. It should flatten out, sorry. Because you hit another 0, so it should flat out. And so the next thing is this. We already find that out. This, at a very high frequency, what is the level of the gain? Which is this. C omega p over omega z, which is C pi, which is 0.1. C mu is, C pi plus C low is 1 pico, so this is 0.1. So you drop to 0.1, which is mainly, as I said, this is when it passed omega 0, it already passed omega t of BJT. So you only see the effect of C pi, C mu. This will be equivalent to your circuit will be approaching this. Input, output. Okay? We don't actually see the active component. We already said the meaning of transit frequency or cutoff frequency is that once it passes this frequency, you see the parasitic effect. The parasitic effect actually dominate, which is C pi. C pi dominate. Charging current dominate rather than collector current. Therefore, you don't see the effect of collector current. Collector current here is GMB pi. That's the collector current. You don't see the modulation collector current effect. Therefore, you will see something like this. The results with an approaching whatever the circuit will deliver. Okay? We can do the same analysis on MOSFET version. So source follower, for source follower, I'm just going to quickly go through. It's actually very similar results. For source follower circuit, your circuit will look something like this, right? So the identical circuit with an ideal current source load, current source biasing and adding to a load. So if we only consider the main capacitance, which is actually this one, CGS, CGD will have very little effect because it's grounded in the other direction. So if you're not considering input effect, then you only see the effect of CGS. So you can actually, we could ignore CGD and CDD because this is much, much smaller than C load. This is the case, then the circuit will be actually easier to construct. So there's only two current compete in charging loading. The summation of two current, once again, there's the feed-forward current coming from capacitive coupling, and then you have the drain current in VGS. This is VGS. So the circuit itself is very simple. You have input. The equivalent circuit, small signal equivalent circuit, V out. So I can simply draw my V out. There's two current components, GM, VGS. Once again, that's the transistor main current, drain current, plus feed-forward current, which is J omega CGS VGS. Okay? So through this equation, we know that this is the current times its impedance, which is J omega C load. That's the output resistance or output impedance, looking at the output delivered by corresponding to C load. So using this, we should be able to get our transfer function as well. Sorry, let me write down V in. V in will be VGS plus VL. So through these two equations, we should be able to get our transfer function once again. So our transfer function, what's wrong with this? The overall transfer function will look something like this. Defined by VL versus V in will then be rewritten as GM, very similar to our previous case. GM, J omega, two components, two capacitive components in parallel. And then this can be rearranged as J 1 plus J omega Z as well, J omega P. So we can rearrange it so that it looks something like this, where our omega Z is once again GM, rather than C prime now CGS as the feed forward. The pole will be at GM CGS plus C load. Okay? In most cases, what happens is that we know that in most, let me just be. As I said, follower circuits are used to drive large capacitance, whether it's parasitic to the circuit or you externally have external device, external components like external pad or external elements. And in most cases, this is much, much larger than parasitic. So this is typically much, much larger than CGS. So in that case, I should say my 0 is to drive internal capacitance. My pole is determined by mostly external capacitance driving capability. So I can also do the same thing. The Bode plot will be very similar. It will start at 1, and then it will hit a pole, and then it will hit 0. So then it will drop by, if I'm assuming my loading capacitance is much, much larger than parasitic, then it will drop to approximately CGS. Okay, this is typically a very small number because this is when your circuit is not actually function as well as you wish. But the bandwidth of the circuit, as I said, for a follower circuit, the dominant, I should say dominant pole, there's actually only one pole in this analysis, is typically omega p. If you think about it as output terminal, which is C load R out, where RL is 1 over GM, that's what you get. So this is approximately C load 1 over GM. That's how you get GM C load. Okay? So your dominant pole, your bandwidth is limited by the first pole and the only pole if you based on this approximation. Okay? So once we get a sense as to what is the limiting bandwidth limited by the comparable, if you think about it, this GM versus C low actually tell us that what is the maximum frequency when the drivability, you provide high enough driving capability to make sure that your bandwidth can extend to a certain level. That means that charging and discharging rate can increase when GM increases. Okay, so the bandwidth actually depending on two things. One is, mostly on one thing, is to increase GM, that's the drivability of your follower circuit. And lastly, I want to talk about, aside from getting the transfer function of a single stage amplifier, there are actually two more things we're concerned about. One is input impedance. So we're going to talk about input and output impedance. I'm going to use the MOSFET version just for now. It will be much easier. So if you think about a MOS follower, source follower, so the capacitance we can see from the parasitic capacitance from, if you're looking in, the input resistance, if we're not consider parasitic capacitance, input resistance is infinite. But if you consider this CGD, CGS, there's also a feed-forward capacitance here is CGS. But we know that in this case, let me just use a fairly easy loading assumption. So we know that between X node X, and node Y, there's a feed-forward capacitance. So what is the gain between X and Y? Vy Vx. The gain is actually GMR load, because it's follower circuit. So if I want to do Miller approximation to find input impedance, should be in output. if I want to find both input and output impedance, first we look at the input part. So the input impedance will then be, if you do Miller approximation, CXY is CGS. And CX is, remember, that's 1 plus A0 times CGS. Here, the gain is no longer, remember, gain here is a positive number, so it's minus A. That means that A0 is minus GM R load, 1 plus GM R load. This is different from inverting amplifier. This is a non-inverting amplifier, meaning that when a follower circuit, meaning input is rising at the very close, output is rising following the input very closely, meaning that I don't need to charge up too much because it's following me. So therefore, it would actually effectively reduce the input resistance, input capacitance. So this would be minus a minus sign. Because we know that A0 now, if you remember Miller approximation, we're using minus gain. So now because this equals to AV, AV is this. This is your voltage gain. Now we have positive inverting gain, positive gain. Therefore, it's a non-inverting amplifier. Therefore, this will be 1 minus GM R load, 1 plus GM CGS. So actually, the CGS will be reduced by GM. That means that the voltage across this is actually reduced because in inverting amplifier, when this rises, this also rises with a small little difference. So you can see that it effectively reduced the load significantly. Okay? So let's say if I give you a, for example, GMR load, let's say GMR load is 10. This will simply mean that my overall input impedance, if I want to find my input impedance, Zn, will simply be J omega C GD plus Cx. Right? And that will be J omega CGD plus, let's say if your gain is, that will be GM R load CGS. So will be effectively less, close to 0.01 CGS. Okay? So this capacitance will be effectively reduced by a gain of 1 plus GMR load. The larger GM is, GMR load is, or if your gain is approaching 0, you're actually not seeing this effect. So if I ask you this, let's say if voltage gain of this amplifier approaches ideal, in an ideal case, or approaching infinite, not 1, approaching 1. Let's say if R load approaching infinite leading to voltage gain approaching 1, what happened is that your input impedance will simply be J omega CGD. Because this will be infinite, you won't actually see this effect, meaning that it exactly follows. Therefore, if it exactly follows, there's no voltage across CGS. Therefore, there's no need to provide any additional charging current. You only need to charge up CGD. There's no charging current through this when this exactly follow, output exactly follow input. Okay? So we get some space for the final discussion. So we still have one item missing, which I would like to address, is output resistance. So let's look at the output resistance. You can do the bipolar version. I believe there is a detailed derivation in the textbook. I'm just going to do the MOSFET one. It's actually slightly easier to get the output resistance. So if you look at this, if we consider output resistance on follower circuits, let me go look at this. Let's say if I'm looking at ZL, it's going to get a sense as to, when we're not considering parasitic effect, what is the impact. So if you're looking at output resistance, which is here, as I'm using that ideal current source as an example just to make sure that I'm looking in from here, ZL. So let's add our capacitance. So this will be CGD. This will be this is CGS. So if you're not considered at low frequency, we know that output R out, but this is simply 1 over GM. Right, that's a follower circuit. But when we include the effect of parasitic capacitance, what happens is that you can actually do derivation based on small signal approximation. The way to do this is this. Small signal model. Let me construct the small signal model. This will be GM VGS connected to ground. And then you look for CGS. Okay. So we're actually looking at this terminal. So what we typically do is that your input is grounded. And then to find ZL, what is being done is that you give it test voltage and look at the test current. So by definition, ZL is Vx, Ix. In this case, we don't actually, because both terminals are ground, so you don't actually see the effect of CGD. You only see CGS. So Ix, if you want to, let me draw Ix. Ix will be consists of this component minus GM VGS. And then this component. This is VGS. So there will be minus plus J omega CCGS VGS. Okay? Now remember what's Vx. Vx in this case is simply, I forgot to add the source resistance. So in this case, if I don't want it to be short, I need to add something to consider the effect. This will bring out the effect. If we consider the source, let me just, your Vin has a source resistance. So that's bringing the effect of Rs. So if you're bringing the effect of Rs, Vx will simply be Ix. This is Ix. This is Ix. So Vx will be Ix times Rs minus VGS. Okay, so once we have these equations, we should be able to construct Vx over Ix. So I'm just going to give the final result. You can do the algebra or simplification on your own. So what we get is, based on this equivalent circuit, we should be able to get our transfer or Z out. Output impedance will simply be a 0 and a pole. You also see a 0 and a pole. In this case, we'll see a omega z at, let me write it down. And then based on this equivalent circuit, we should be able to get our omega z determined by RS CGS. And omega p will be GM CGS. Okay? So this is the case, then we should be able to do the Bode plot of the overall impedance change as frequency. So if you look at the impedance change, we look at the magnitude. Let's just look at the magnitude of the change. If you look at the magnitude of the change, what happened is that if you look at this, typically what we will be experiencing is that you will then experience a omega z first. In this case, this is very high frequency, so typically omega z will be lower than omega p. So we know that we have omega z here, omega p here. We already know we will then see the 0 first and then see the pole later. And then the next thing we want to know is, of course, the boundary at very, very high frequency and very low frequency. So if you look at this, let me write down z out absolute value is 1 over gm square root 1 plus omega p squared 1 plus omega z squared. So this is the same thing we do for when we analyze the gain. Which one to do this with? So what happens is that you look for, when frequency is very, very low, you don't see this component. So at omega smaller than omega z and omega p, you see 1 over gm. So that's our low frequency behavior starting at 1 over gm. And then once it hit omega z, you can use the Bode plot approximation. Once you hit the omega z, what happens is that it will start rising at a rate of plus 20 dB per decade. And then once it hits the pole, it should flatten out. Okay? So we're interested in finding out what is the ultimate limit. There's two ways of doing this. One is using the ratio. The other is using this equation. It should be consistent. So let's do it with Bode plot. So if we use Bode plot, we know that it will increase with this level. Should be 1 over gm times omega p over omega z. Okay? So it should be this. So it's 1 over gm omega p, which is gm CGS. And omega z is 1 over RS CGS. Okay? So if you do this ratioing, we cancel this, cancel that. And finally, it should be RS. Right? So eventually, this would then rise to a level of RS. So what does this mean? That your input impedance is either this simply, if you want to get an intuitive sense as what it means, is that this is when transistor is still functioning. When it passes omega p, this again transit frequency, past the transit frequency of the transistor, you don't see the transistor, you only see RS. So it's like a short between the two. So this is omega larger than omega t. You don't see the effect of collector current, which is 1 over gm. 1 over gm is because there's collector current. You don't see the effect of collector current. The whole thing between source and drain is dominated by this capacitance. Therefore, if it passes this frequency, meaning this can be viewed as a short, so you actually see a short between these two terminals. That's why eventually you get to RS. Okay? So what is the significance of this is that you will see something, if you look at this will give you something behave like an inductor. So in this case, my ZL, the absolute value of ZL increases as omega increase in this regime between here. So if I'm operating in this part, you will see significant output resistance increase as omega increase. So what component will have this characteristic, which is will be we call the active inductor. What I mean by active inductor is that if you don't want to, for a lot of oscillation circuit, for example, LC circuits, you need capacitors and you need inductors. Inductors is actually very hard to make in integrated circuits. So if you don't want to actually build an inductor, you can use this circuit to sort of simulate an inductor or to actually make something that looks like an inductor behavior, so to get oscillator or other inductor applications. So that's not a real inductor, but a circuit simulated inductor. So these are typically refers to as this we call it inductive impedance, where you see as frequency increases, your impedance increase, therefore it will be used as an active inductor sort of application. Okay? So finally, we get a sense. So we can fill back the final summary here on follower circuit. So lastly, on follower circuit, what you need to know that is that its bandwidth is limited by pole, by omega p, which is typically the GM, which is for designing how well this follower drive the output, and then depending on loading capacitance. So this is typically the loading. So if you wish to have high enough bandwidth, you need to make sure that drivability of the circuit is high enough in order to extend the bandwidth of the follower circuit. Otherwise, it would become no longer an active circuit once it passes omega p. So it will no longer provide an active driving capability by the transistor itself rather than capacitive coupling. So this is one of the important things we need to understand. And then the second thing I want to emphasize is that Miller cap Miller capacitors is reduced by by the follower circuit. So your feed-forward either C pi or CGS is reduced by a factor of 1 plus gain. I shouldn't use the gain. 1 plus GMR load instead. That would be actually more general. Okay? So that's what you need to know about single-stage amplifier. Once again, I want to just give a quick summary as to what you need to know. So what we expect you to be able to answer. For example, if I give you a circuit, you should be able to find out at least its pole referring to a particular node. For example, like input pole or output pole, or the dominant pole. These are the key important things. So we have already addressed that. We're probably not going to talk too much about zeros. Zeros are very hard to predict. Typically, at a much higher frequency, you will see the effect of zeros. So typically, what we want is for you to be able to identify where the pole is, and of course, which one is the dominant pole. And once you hit the pole, what kind of effect will it had on your transfer characteristics? Okay? 好，那我最后就做一个简单的 summary， 就是针对 single stage amplifier 的 frequency response， 你需要知道什么，或者我们考试的时候会考什么东西，就是你要知道说，如果有 input 跟 output pole， 通常 single stage 就是 input 跟 output pole， 所以 input pole 和 output pole 分别通常 input 的 terminal 跟 output terminal node 都会 introduce 一个 pole， 所以你要可以 identify 他们的 pole 的位置，跟它跟什么东西有关。那我们大概考试不太会考低频那一段，因为低频那一段会比较复杂一点点，所以大概就是偏高频的 parasitic 的 capacitance。那你要知道，我们给你 parasitic capacitance， 你要能够算 input 跟 output 的 pole 位置在哪里，然后再来就是要知道哪一个是 dominant pole， 通常哪一个是 dominant pole。然后当你遇到 dominant pole 的时候，会发生什么事情？就是会有 3dB。那在这个点上，你的频率反应是什么？你的 gain 是多少？这些东西大家要能够掌握，这样子。OK， 好。那 I think I'll probably just wrap it up here, and then now we're gonna open up for questions. If you have any questions, please bring it up, and I'll try to answer it here in class. 那我先从第一题回答起来啊，就是什么叫做一般应该是讲说，你回到 transistor 的本身哦 ，transistor 本身呢，就是说大部分所以一般讯号看电压的问题，是因为我们在电路的电子系统里面，通常我们都是用电压作为讯号的来源。所以如果你要比如说我们在讨论 intrinsic gain 的话，我们就是看 voltage gain， 好，那就是看 input output 的这个 voltage gain。那可是呢，如果你要回到 transistor 本身的时候呢，我们在考虑 transient frequency 呢，通常这个我先讲一下，我们通常是看所谓的 short circuit current gain， 不是 open circuit， 而是说 open circuit 就没有 current 了，就是那原因主要是因为大家可以想象啊，就是如果说我把它转换成电压，任何时候你要把东西转换成电压呢，就是我 input 要转换成电压，假设 input 是电压，但是 output 通常是应该是说 transistor 本身哦，它最重要的 component 叫做 GM。transconductance 的意思是什么？它 deliver， 它让我们可以看到你的 output current， 不管是 collector as an output current， 或者是 drain as an output current， 它是 GMVN。所以我们一定是看 output 的 current， 因为你的 gain 呢会跟你的 loading 有关，就是 output VL 会等于 IL 乘以 RL 嘛，所以跟你的 loading 有关。那当你 loading 改变的时候，你 output 跟着变，这个大小就没有意义。所以你要回到 intrinsic 的 sense 的时候呢，你就要回到这个 loading 是没有 loading effect， 就是你不希望看到 loading effect， 所以你就把这个设成0，然后回去看 output current。那为什么我们在看频率响应的时候会比这个东西呢？第一个就是一个是 output current 呢，通常是 就是你会看到最后，它就是比主要你去开水的时候的那个水。所以呢，你 output current 你就是比你的 output I/O 嘛 ，I/O 就是我们讲 GM the modulation。那当你要推的时候，就是你要推，所以这个是你的 performance。transistor 的主要的 performance 呢，就是 transconductance。那我们刚刚讲，你要把它变成电压，就是跟 loading 有关，所以你希望是跟 loading independent， 所以你希望看的是 output current。那另外呢，那 input 端你的代价就是要比较电，也就是你要除以一个 base 嘛，除以一个 base 就是 input。那特别在高频的时候呢，我们就会有 input 呢，就会有 input 的 charging current 会 dominate， 所以你的代价主要是来自于 input 的 charging current。那 input 的 charging current 呢，所以这个就是 I in 呢，通常就是你会发现大概就是 J omega C in。所以最终呢，你就是去比较说，我到底要灌多少水跟 output 的比较。那主要是因为当你在高频的时候，你主要看到的就是 charging current 的 effect。所以呢，你比较的就是电流跟电流比，就是 output 也是看 current，input 也是看代价。所以主要是这个样子。我不知道这样有没有表现。那之所以 short circuit 就是你不希望看到 loading 的效应，那因为 current 当然是跟你放进多少 current 比，所以就是电流跟电流比。所以我们看 short circuit current 电。那再来，对，充满电。你要想象一件事情，就是你的 CXY， 你的 Q。假设我是有一个电容，我们如果用 XY 来看，那这边有一个 CXY。那所以呢，你的 Q 在这个我用 V4 啊，你想象这个 Q 要在这个 V4 capacitance 上面是 CF 乘以 VXY， 所以当 VX 上升的时候 ，VY 下降，的确 VXY 会上升。那 VXY 上升表示什么？你需要更多 Q 啊，表示 Q 要比较多。Q 就会增加 ，Q 增加代表什么呢 ？I 必须要增加 ，charging current 你进来的这个电流要增加 ，I charging 要增加 ，I charging 要增加，自然就是电容会变大。它并不会更容易达到饱和，因为你想想看，你要冲水，你只要想水桶就好，你要冲水。水桶的一个上面，就假设一个是水槽好了，水槽的上面是你想要把那个电位，什么叫做充电的效应？充电的速度，就是水灌进去，这个水提起来的速度。如果另外一边再往下掉，你是不是要灌更多 X 才可以上来？所以这是 effective 的效果。也就是你需要更多 charge， 所以 I charge 就要上升啊。所以你会看到 CY， 就是 input terminal 看到拉不动的现象。你只要看到这个不是叫做更不容易充满电啊，因为你要充更多，因为另外一边在 sync 啊，就是我之前讲猪队友，就是一边上面一边下面，这样子就是猪队友，因为我要灌更多水，我才可以在 input 端看到它往上提哈。那这个跟 follower 刚好像 ，follower 是一起走就是有人帮你啦，就有一个后面有个助力，所以跟着走的时候，那你根本不需要灌多少，你需要灌的越少，电容越小。等效电容越小，需要灌的越多 ，charge 越多，等效电容越大。电容是 QV 啊，对不对？所以 Q 越多，电容越大。你 input 端看到的 effective 电容。那再来最后一题呢，就是这个是有一点 tricky， 就是说我们其实没有讲得很详细哦，就是说真正的。应该这样说，如果你看 FT 就是 long channel， 我们通常讲 long channel。long channel 的状况呢，就是我会发现呢，我的 GM 呢会 proportional to， 如果我们看 μNCox W over L VGS minus VT。这是 long channel 的特性，因为它的 GM 是这样子，所以呢，我们最终呢就会得到呢，你的 frequency 呢会跟 gate length 呢成 square 的关系。 那如果是 short channel 呢？我之所以为什么说 not necessary true for short channel， 是因为 short channel 的状况呢，你会发现当 channel 非常非常短的时候，你的 GM 呢会 proportional to 就是会跟 L 没有关系啊。就到后来呢，它会有一个 saturated 的速度。这个大家如果有兴趣，未来可以修固态电子元件，会告诉你说，最终的速度呢是跟长度跟电场没有关系，它就有一个最快的速度。所以它会这边这个 L 实际上是 stand for 电场的速度的那个微分。那所以呢，当你变成这样的话，就是没有 L 的话，那最后就会导致 FT 呢就会看到类似这样，就非常非常短通道会变成这样。所以呢，如果你要更高频的话，只是说掉的不会那么快。也就是说，如果我今天是0.5跟0.3，那我可能呢，我的频率呢就可能差4倍。0.5跟0.3是差4倍，可是呢，我如果是就是45奈米跟28奈米，我的频宽可能就只差2倍，因为我已经回到这个 dependency。所以这个问题呢，就是说你可以到非常非常 short channel， 只是你越往短的，就是说。我这样讲哈，就如果说这是 FT 好了，那这是长度，那所以呢，我在这边呢可能下降，我看看我怎么画，对，它下降幅它是 square 的下降，到后面它就变线性的下降，所以这边是比较长，假设是 long channel， 我画这样大家可以看到，就是我画它可能有2个区域嘛哈，就是频率跟 L 的关系呢。因为我这个图看起来可能不会很那个，就是 1/L， 这边是 1/L， 1/L 应该也是有点这样的，或是我画，我不知道怎么画会比较好，就是假设我画 1/L 哈，那 1/L 右边就是比较短通道嘛，所以短通道它这边就会是线性的上升，到这边呢是。有点像这样子，就它会比较上升的幅度是不一样的，就它的 slope 会不一样。这边是正比于，这边 FT 呢是正比于，这是短通道。那长通道呢 ，FT 呢就会正比于 L square。我不知道我这样画是不是 L square， 应该是吧？所以呢，就是你会有2个区域啦，这是 long， 这是 short， 因为是 1/L 嘛。那这边是 long channel。所以当你就会有 dependency 不同的，但是你还是可以透过缩短让你的频率增加，这件事情还是会发生，只是速度没有那么快而已。OK。